Good afternoon. We had completed our discussion on magnetic circuits in the last class. So I'm going to do a couple of problems in BH loop, after which we will have a little bit of coverage of transformers, and then we'll try to do one problem on that. So the first problem what we are going to discuss, it is going to be stated as follows. The area of a hysteresis loop for a certain magnetic material is 160 centimeter square. 160 centimeter square with the following scale. So the scale of X and Y axis are given here. X axis 1 centimeter equal to 25 ampere per meter, and Y axis 1 centimeter equal to 0.1 Tesla, 0.1 Tesla. Okay. Now what is being asked is calculate the hysteresis loss in watts per kg. If the excitation current has a frequency of 50 Hertz. And the density of the magnetic material is 7,600 kg per meter cube. So this is what is given as the problem. So if you really look at the hysteresis loop, what we had drawn in the last class, let me draw it once again. So we had drawn it somewhat like this. If I'm going to have H along the X-axis and B along the Y-axis, if this is the way it is, I'm going to have, if it is a new sample of iron, I'm going to have the characteristics somewhat like this. This is what we drew. And then when you try to reduce H, you're going to have the magnetization characteristics somewhat like this. This is going to go up like this and then come down like this. So this is the complete BH loop. And what is given here is the H scale is 1 centimeter equal to 25 ampere per meter. That is what is given here. And in Y-axis, the scale is given as 1 centimeter equal to 0.1 Tesla. This is what is given in the problem. And the area under the loop is given to be 160 centimeter square overall. Right? This is the data that is being given. And in the last class, we said that the area under BH loop is actually representing the hysteresis loss. That is the loss that is incurred in the material due to aligning and realigning the magnetic moments. That's what we said. So this will be hysteresis loss in joules per cycle, because every cycle this loop is going to be traversed, and per meter cube. because we are talking about flux density, which is per unit area, and we are also talking about the magnetic field intensity, which is per unit length of the magnetic circuit. So that is the reason why we call this as the area under the BH loop represents the hysteresis loss in joules per cycle per meter cube. So first of all, let us try to calculate that. So we will say joules per cycle per meter cube. What we can calculate as hysteresis loss will be 160 centimeter square multiplied by the scale of the x-axis and y-axis in terms of what is being represented by 1 centimeter. So that is 25 ampere per meter cube multiplied by 0.1 Tesla. Okay, so this is going to be the loss, the energy loss, which is in joules per cycle per meter cube. And what is given is 50 Hertz is the frequency and the density is 7600. So if I say J per cycle per meter cube is multiplied by cycles per second, which is actually the frequency. Okay, so what we represent here is basically Hertz. This is the frequency. So that will give us joules per second, which is watts, and it is going to be per meter cube. Okay, so this is essentially watts per meter cube. That's what we are going to say if we are actually multiplying this by the frequency. Now this watts per meter cube, what is available, if I divide this by the density, then I'm going to have kg per meter cube. So I will have this meter cube, dimensionally this meter cube and this meter cube will get cancelled with each other. So I will get watt per kg. So if I want ultimately watt per kg, hysteresis loss in watts per kg, then I have to multiply by the frequency and divide by the density. That's what we have inferred now. Okay, so I should say hysteresis loss in watt per kg will be obtained by area under the loop, under BH loop, multiplied by scales of B and H. We have to multiply by the scales and then we have to multiply by the frequency in Hertz and we have to divide it by density. So if we do that, so rather than writing Hertz, let me write this as frequency. So let me multiply this by frequency and divide by density. Now what I have got here is 160 multiplied by 25 multiplied by 0.1 and this has to be multiplied by 50, which is 50 Hertz, and divide by whatever is the density. Density is given to be 7600. So I'm going to divide this by 7600. So this will directly give me what is the hysteresis loss in watts per kg. And this is coming out to be 2.63. So what you get here is 2.63 watts per kg is the hysteresis loss of this particular magnetic specimen. Okay, so that is what is being given here. Okay, any questions on this? Any questions? Is this clear? This is essentially from what we discussed earlier in terms of BH loop and how that is representing hysteresis loss. So we are calculating from the BH loop. Ultimately, if we want hysteresis loss, the losses are generally calculated in I square R in a resistive circuit, which will be in terms of watts. The same way we want to have it not in the form of energy loss, rather what is the energy loss per second. So that is the reason why we are expressing this in watts. So we are expressing this in terms of watts. But because we have divided this by the density, we have got what is the loss per kg in a particular material. That's what we have got. Okay, fine. Any questions? So if there are no questions, let us try to proceed to another problem in hysteresis laws, and after which I'll resume transformers once again. Okay. So in problem number 2, this is the statement of the problem. A hysteresis loop is plotted. A hysteresis loop is plotted with magnetic field intensity H in x-axis, and the scale is 1 centimeter is equal to 1000 ampere per meter. Okay, and B in y-axis, that is the flux density in y-axis, and y-axis has a scale of 1 centimeter is equal to 0.2 Tesla. Okay. So a hysteresis loop is plotted with H in x-axis and B in y-axis. It has an area of 9 centimeter square. Overall height of the BH loop is 14 centimeter. Calculate A hysteresis loss in joule per cycle per meter cube. So the first thing that is being asked is hysteresis loss in joule per cycle per meter cube. The second one is peak flux density as per the graph. C is hysteresis loss in watt per kg, watts per kg, assuming the frequency of the excitation current as 50 Hertz and the density of the material to be 7,800 kg per meter cube. Okay. So let's first of all again draw the hysteresis loop. So if I draw the hysteresis loop, I have to draw it somewhat like this. So this is going to be the complete hysteresis loop what we see for a magnetic material. So this is going to be H and this is going to be B, and the entire height what they say is going to be 14 centimeters. So this entire thing is, and assuming it is symmetrical, so this is going to be 14 centimeter as per what is specified in this particular problem. Okay, So if you look at it, what is the hysteresis loss in joules per cycle per meter cube? That is what is being asked. So joules per cycle per meter cube directly is given by the area under the curve, and which is 9 centimeters square. So I should say here hysteresis loss in joule per cycle per meter cube is going to be equal to 9 centimeters square multiplied by 1000 multiplied by 0.2. 0.2 is 1 by 5. So this is 9000 divided by 5, which will be 1800 joules per cycle per meter cube. Okay, so that is the answer to the first subdivision. The second subdivision is asking what is the peak flux density as per the graph. So the total height is 14 centimeter. Okay. So that means on either direction the excursion is about 7 centimeter. So we should say B max equal to minus B max, which is going to be on the other side. That will be equal to 14 divided by 2, which is 7 centimeter. So if I try to use the scale 7 centimeter multiplied by 0.2 Tesla, that is going to be essentially 1.4 Tesla. So we are going to have either B max or minus B max. Minus B max will be minus 1.4 Tesla and B max is just 1.4 Tesla. So the maximum flux density, what we see in the graph, from the graph should be 1.4 Tesla in either direction. Okay. Now part C is similar to what we did in the last problem. So 1800 joules per cycle per meter cube has to be multiplied by the frequency and it should be divided by the density to ultimately obtain the losses in watt per kg. So we can calculate this as 1800 multiplied by 50 divided by 7800. Okay, so this is going to be the overall hysteresis loss per kg of the material. So that comes out to be 11.54 watts per kg. This is actually the hysteresis loss in terms of watts per kg of the magnetic material for which we have drawn the BH loop. Okay. Any questions further? Anything? Any questions? So these are the two problems I wanted to work out in this particular class so that you get familiar with the hysteresis loop. So now let's try to resume what we were talking about transformers in the last class. So as I told you, transformers is the first or static electrical machine where there is hardly any moving part. So this is a static electrical machine which is mainly used for stepping up or stepping down the voltages. So this is essentially meant for either increasing or decreasing the magnitude of voltage, which is meant for either stepping up during transmission. From generation, you want to take it to transmission. Normally, generating stations have a voltage level between, the voltage level is generally between 10 kilovolts to about 25 kilovolts, maximum 30 kilovolts, not more than that. This is the voltage level at generation. Whereas when you look at the transmission level voltages, as I told you earlier, the power that is being transmitted is a product of voltage and current. Of course, there will be cosine of the angle between these two. But voltage and current ultimately determine how much is the power that is being transmitted. So if I try to step up the voltage, if V is increased by stepping up, then correspondingly you are going to have I coming down. I will be decreased automatically. So if I is decreased, you are going to have mainly two advantages. If I is small, if the current is small, the thickness of the conductors will be decreased, because generally copper also has a limit of how many amperes it can carry per centimeter square. So if the current carried is smaller, then the thickness of copper conductors can be decreased. That is one major advantage you are going to see. And the second thing we can say is, if we are going to have basically lower current flowing through the conductor, we will have I square R losses in the transmission line can also be decreased. So we are having mainly two advantages whenever we want to transmit the voltages at transmit the power at high voltages. So that is the reason why generally we are going to increase the voltage. So the voltage will be increased something like 465 kV, 800 kV, and 440 kV and so on. So there will be very large voltages at which the transmission will be taking place. So generally for that purpose a transformer will be used. Similarly, when we talk about the distribution end, finally when it comes to houses or any industry, you are going to see that the voltages first of all from 465 kV or something, it is stepped down to either 33 kV or 11 kV. And from here it may be further stepped down to 400 volts three phase or 230 volts single phase. So this is what is done at the distribution end. So this is going to be step down action. Whereas at the transmission end, it is going to be step up action. So this will be stepped up from generation level to transmission level, and at the distribution end, it will be stepped down from the transmission level to distribution level or domestic level. So this is what is going to happen. So transformer plays a very vital role in power transmission and distribution. Without transformer, it would not be possible for us to have AC transmission at all. Okay. So if we normally look at the transformer, we can say voltage, let us say, is stepped up, but the power cannot be amplified unless you have something like an amplifier. So automatically if voltage is stepped up, then current has to be stepped down, because the same power has to be retained on the primary side as well as secondary side. So the current has to be stepped down. This is the way normally the transformer works. Whenever you are going to step up the voltage, correspondingly you are going to have the current being stepped down. So whenever we talk about a transformer, as I told you in the last class, notionally you can say transformer structure somewhat looks like this. So I'm going to just say about the construction very briefly. So I'm going to have for the primary and secondary, they have to be wound around a ferromagnetic core. So I'm going to have probably my ferromagnetic core somewhat like this. So I'm showing the shape of one particular stamping. Let us say we call this as stamping. And behind this, I'm going to have one more stamping, which is, arranged or stacked. So I'm going to have the next stamping. Then I'm going to have a third stamping. So like this, I'm going to have many of them, many such stampings. They are going to be arranged one behind the other, but between two stampings, generally we will have insulator. So the two stampings generally will be insulated from each other by varnish coating, or maybe we will have a thin sheet of paper, maybe we will have chalk powder, maybe we will have some kind of cloth. So we will have to have some kind of insulation between the two layers of stamping so that the current does not have a thoroughfare. You will not be able to pass a current through the stamping like this. That will not be possible. So this will avoid thoroughfare of current or free flow of current in the core will be avoided or will be prevented by having this kind of insulation between two adjacent stampings. So these can be called as stamping, or some people call it as lamination. So you are going to have multiple laminations, and the laminations will be stacked together with insulator in between, and then it is made in the form of a complete core. So this is the core. Now inside this core, around this core, you are going to have the windings wound like this. So you are going to have the windings going around like this, and then that is taken out here. So this is going to be, let us say, the primary winding, and I'm going to apply a voltage of V1 here. And this is N1 is the number of turns in the primary winding. The same way I'm going to have secondary winding again. So I'm going to have the secondary winding also going around like this. So I'm going to have this winding coming out like this. So this is, let us say, secondary, and I'm going to have N2 turns here. Okay. Generally, we call these two portions which are actually having the winding, these two we call as limbs. These are the vertical structures around which we are going to put the windings. And the windings will also be insulated so that the current is not going to flow from the winding into the core directly, because the windings will also be surrounded by its own insulation. And these two portions, the horizontal portions, are generally called as yoke. So this is known as yoke, and these vertical portions are called as limbs. Okay, so you are going to have the windings wound around like this. Like what I told in the last class, I'm going to have a flux established here. Maybe the flux is established somewhat like this. I'm going to have a flux established which is flowing through only the ferromagnetic material as much as possible. So this is going to be the path for the flux. So I'm going to have the flux flowing around like this. So whatever flows in the primary, the secondary is also going to see or face the same amount of flux. So if I talk about what is the EMF induced in every turn of the primary as well as secondary. So EMF induced in every turn of the primary and secondary coils. If I try to write that, that will be d phi divided by dt. If I'm talking about this flux as phi, if I say that this flux is phi, So I'm going to have d phi by dt as the induced EMF. And according to Faraday's law, we know that the total voltage induced, if I try to write what is the total voltage induced in any coil with n number of turns, that is going to be equal to n d phi by dt as per Faraday's law. So we are going to have, as per Faraday's law, the primary coil induced EMF is going to be N1 d phi by dt, whereas secondary coil induced EMF is going to be N2 d phi by dt. So I would say, if I talk about primary coil induced EMF, this is going to be N1 d phi by dt. And similarly, secondary coil induced EMF E2 is going to be N2 d phi divided by dt. So that is the reason why we can say E1 divided by E2 is equal to N1 divided by N2. And after all, if this particular coil is going to have hardly any resistance, it is a thick copper coil, it's not going to have much of drop or anything. So I can say V1 and E1 should be approximately equal to each other. And in the secondary side, I have not connected any load, and I'm going to measure V2 as the secondary terminal voltage. If there is no current at all in the secondary side, if I have not connected any load, I'm not going to see any voltage drop. So I should say E2 and V2 are exactly equal to each other when no load is connected in the secondary. Okay, so if no load is connected in the secondary, I'm going to have E2 to equal to V2. So I should be able to write this as approximately V1 by V2. Instead of writing E1 by E2, I can write this as V1 by V2, where V1 is the applied voltage on the primary side, which is almost equal to the induced EMF because there is not going to be much of resistance drop. And V2 is going to be exactly equal to E2 when there is no current drawn from the secondary side. So I have the equation basically V1 divided by V2 equal to N1 divided by N2. This is going to be the equation, voltage equation of the transformer. Another major advantage of using a transformer for stepping up and stepping down action is generally the efficiency of a transformer is extremely high. The efficiency of this kind of ferromagnetic material based transformer, that will be greater than generally 95%. In fact, it can go up till easily 99%. So you will hardly see any loss going from input to the output side. So if I say that V1 I1 is the input volt ampere, please note I am not saying wattage, I am telling volt ampere, because what is the displacement between the voltage and ampere depends heavily upon what kind of load I am going to connect here. If I connect an inductive load, voltage and current will be related in such a way that the inductive current lags behind the voltage. If I connect the capacitance, then I'm going to have in all probability the current leading. If I use only a resistance, in all probability I'll have voltage and current being in phase with each other. Okay, so that is the reason why I cannot predict what is cos phi. Cos phi depends upon load. I cannot say what is cos phi value unless I know exactly whatever is the load that is being connected. Okay, so this is input volt ampere, what is available from the primary side, which I am pumping into the transformer. that should be approximately equal to V2 I2, which is the secondary side volt ampere, because I hardly expect any loss to take place within the transformer. So from here, I should be able to say V1 divided by V2 equal to I2 divided by I1, which is also incidentally equal to N1 divided by N2. So this is generally the voltage and current relationship in a transformer, which is actually excited by alternating current, and the secondary side, it is going to be connected to a reasonable load. What do we mean by reasonable load? If I say it is a 2.2 kVA transformer, I would be drawing a current that is close to maybe 2.2 kVA, such that the output delivered is close to 2.2 kVA. So I'm neither talking about completely open circuit condition nor talking about almost short circuiting the secondary. So it is exactly whatever is the reasonable amount of volt ampere I am supposed to deliver to the load. The transformer is essentially expected to deliver that kind of current. Under such an operating condition, if I try to look at the relationship, this will be a valid relationship normally. Okay. So I can say that V1 and I1, V1 is directly related with N1, whereas it is inversely related to N1 as far as the current is concerned. So let me again take up the transformer with a core what I had shown earlier. I'm deliberately showing it here as though it is kind of thin and tall. So this is the kind of transformer core I'm looking at, and I'm going to have the primary wound here, and I'm going to have the secondary wound here. So the primary is applied with the voltage of V1. So I have applied a voltage of V1. So when it is applied with the voltage of V1, I'm going to have a small current flowing. The current may not be very high because to establish the flux in a ferromagnetic material which is having low reluctance. So if I try to look at the transformer action, I normally have only ferromagnetic material as the core, so that the current that is being drawn here, that is going to be really minimal. So this current is going to be minimal. With very small current drawn, I'm going to have a flux established. I'm showing only one line, but there will be many lines that will be sitting here. So this is going to be the flux that is established. Now, after the flux is established, the secondary is going to have definitely an induced EMF. I call that as E2. And I call this voltage as E1. So I expect that V1 and E1 are almost equal to each other, and E2 and V2 will be equal to each other as long as I am not drawing any current from the secondary side. Okay. Now I'm going to connect a load to the secondary side. Let us say I'm connecting a load. I'm not saying what kind of load it is, whether it is inductive, capacitive, resistive. I'm not telling anything. I've connected a load here. The moment I connect a load, I will have a current flowing here, which I may call as I2. I2 is the current that is flowing through the load from the secondary side. The moment one I2 is established, this is again not going to keep quiet. This will also establish a flux in the core because this is having a current, and I will have some dots somewhere and cross somewhere. Maybe I will have dots here and cross here, for example, and I'm going to establish a flux because of this. Please note this flux will be established in such a manner that it is going to go up like this. So these two fluxes will oppose each other. In fact, The flux established by the secondary has to oppose the primary flux. If it is additive, the flux would have gone to infinity, literally. Because you will have more flux, more induced EMF and more current, and then further more flux and more induced EMF. So it should have essentially gone to infinity. That cannot happen in nature. That is the reason why, let us say, first primary excitation is applied. I'm just writing step by step the working of the transformer. Primary excitation is applied. This causes a current flow in the primary winding. Because of the current flow, I am going to have a flux is established. In the core. Okay. Now I'm going to have the secondary winding faces this flux. Mutual flux. So induced EMF, which is equal to, let us say, E2, that is going to be induced in the secondary. Okay. Now let us say I connect a load. So I'm going to connect a load is connected in the secondary. Load is connected across the secondary. So a current of I2 is drawn by the load. So this is going to establish a flux which is going to oppose. So by Lenz's law, I2 establishes a flux in the core. This opposes the original flux. So the tendency will be to kill the original flux if it is possible. Please remember, what is going to happen is when I am applying a voltage of V1, let us say 220 volts or something, I'm going to have a very small current drawn here because I'm going to have a huge induced EMF. Even for a small amount of flux, a small amount of current, a good amount of flux will be established because the reluctance is low in ferromagnetic material. So there is going to be a good amount of induced EMF here, what I have shown as E1. So this is going to be almost equal to V1. So hardly any current will flow here. Very small current. Whereas when I connect a load here, maybe if I talk about this transformer as 220 volts slash 110 volts transformer, I will be getting about 110 volts here. But for 110 volts, I might have connected probably 11 ohm as the resistance, or maybe 5.5 ohm as the resistance. So I'm going to have a good amount of current flowing. So the current flowing could be as high as 10 or 20 ampere. So this is definitely going to create a flux which is opposing the original flux. So in all probability it can kill it completely. So the moment the flux, the mutual flux decreases even slightly. So we are going to have the flux decreasing. So the mutual flux decreases even slightly. You are going to have E1 smaller than V1. So a larger current would flow in the primary. And If a larger current flows in the primary, its flux is again going to increase. What was being originally killed by the secondary current, that will again rise. So this will happen repeatedly until this flux, which is actually established in the core originally, will be in a position to reinstate itself. It has to remain there. Otherwise, the transformer action itself is going to be completely stopping. It is not going to take place. The transformer action is not going to take place. So the mutual flux, or the flux created by primary, originally whatever was in the core, has to sustain. Otherwise, you are going to have the transformer action completely ceasing, or it is going to stop completely. So this has to sustain. If the flux has to sustain, if this is taking 20 ampere, whereas this was taking only about 0.2 ampere, now this current has to almost raise to the same value as that of this, or at least I should have the MMF from this side to be equal to the MMF from this side. Both MMFs almost have to be equal to each other so that the original flux survives. So I am going to see that generally if N2 I2 is the current drawn from the secondary side, or MMF from the secondary side, I should have the primary side MMF almost equal to this, because the original current what was being drawn as 0.5 ampere or 0.2 ampere is really meager as compared to this 20 ampere. So I'm almost neglecting it. All I'm saying is whatever current was drawn by the secondary, which was trying to kill the original flux, will be counteracted by an additional current drawn from the primary side, which will actually counteract the secondary side MMF. So I'm going to have an N1 I1 drawn, where I1 is again an increase in the current that I have seen on the primary side, such that the original flux remains undisturbed. That is not going to be killed. Whatever was trying to kill it, the secondary current was trying to kill it. To counteract that, the primary will draw a larger current such that the primary MMF and the secondary MMF become almost equal to each other. So I will have the MMF on the primary side and the MMF on the secondary side. Both of them will be equal to each other, almost equal to each other, because the initial current drawn for establishing the mutual flux in the core was negligibly small. So I'm going to have these two, N1 I1 equal to N2 I2, from which I should be able to write N1 by N2 equal to I2 by I1. So this is the current relationship for the primary and secondary of the transformer in terms of the number of turns. Whereas if I try to look at the voltage relationship, that is directly from Faraday's law. There is no second thought about it. It is going to be essentially V1 by V2 equal to N1 by N2. This follows directly from Faraday's law, assuming that there is a common flux which is existing in between the primary and secondary. Okay, so in a transformer, the voltage induction in the secondary side is because of magnetic coupling between the primary and secondary. There is no direct electrical connection. This is one of the major advantages of the transformer. The transformer does not have a common ground existing between the primary and secondary. The primary and secondary are not electrically connected at all. They are essentially interacting with each other because of the magnetism that is existing between the primary and secondary, the magnetic coupling that is existing between the primary and secondary. And to make sure or facilitate this magnetic coupling, we use ferromagnetic materials as the core for the transformer. So all the electrical machines as well as transformers use ferromagnetic core, because always the conversion from the primary to secondary, or from the stator to rotor, or from the rotor to stator, it always takes place because of the magnetic wire media existing between the primary and secondary, or between the stator and rotor coils. So that is the reason why all the electrical machines are normally made up of ferromagnetic material. The core will always be made up of ferromagnetic material. The core has to be made up of ferromagnetic material, otherwise the reluctance will be too high. If the reluctance is too high, then it will require more and more current to establish the flux. And even after establishing the flux, you cannot say all the flux that is established by the primary will completely be coupled to the secondary side as well. That may not be coupled, because very often you may have leakage that is taking place every time you are going to have a transformer or any other electrical machine made up of non-ferromagnetic material. Okay. In a transformer, if I say that the flux is going to be phi m sine omega t, because I am actually giving a sinusoidal voltage, so I'm going to have sinusoidal current. So if the sinusoidal current is flowing through the transformer, the flux is going to be sinusoidal as well. So this is going to be the flux. So as per Faraday's law, I can say d phi by dt is the induced EMF or induced voltage per turn in both primary and secondary. So omega we know is 2 pi f. So I should be able to write this as d phi by dt equal to 2 pi f phi m, and sine omega t can be specified as now cos omega t, because after differentiation. So this is going to be the induced EMF per turn. So this is going to be actually the peak value. What I get here, this one is the peak value of voltage per turn. Okay. So if I try to look at what is the RMS value of voltage per turn, I have to divide this by √2. So I should be able to write this as √2 times pi times f times phi m, where phi m is the peak value of flux. So now I can get this as √2 times pi is actually coming out to be 4.44. So I'm going to have 4.44 multiplied by frequency multiplied by phi m, where phi m is the maximum flux or peak flux that is established in the core. So the flux has a direct correlation with how much voltage is induced. Lower the flux value, I'm going to have lower voltage only induced. So if I want a good amount of flux to be established, I will need ferromagnetic material which require very, very small amount of, which carry only a small amount of reluctance. So I can say primary voltage from this equation, I can say primary voltage is 4.44 f phi m multiplied by N1, where N1 is the primary winding turns and secondary side voltage is going to be 4.44 f phi m multiplied by N2. So N1 as well as N2 depending upon how many number of turns my primary winding has or the secondary winding has, I'm going to have correspondingly the voltage induced adjusted as per the number of turns. That's how you get either step up action or step down action.